Thanks for joining us on this evening for the Chelmer Valley webinar on SUDS. My name is Anthony Pasquini. I'm General Manager at Chelmer Valley, and tonight's presentation will be presented by our Technical Manager, Mike Jepps. Our main focus tonight is to impart our knowledge and experience, hopefully making you aware of the design considerations and terminology, and how to avoid frustrating, lengthy planning permission delays by incorporating a permeable front driveway construction. If anyone has any questions throughout the presentation, if you could just pop them into the chat, the live chat, and we'll get to those at the end. We'll run through them. And finally, if everyone could please remain on mute during the presentation, it'd be greatly appreciated just to stop any background background noise, because we are recording tonight as well. So yeah, I'll pass you over to Mike, and he's going to go over everything with you, and then I'll run through the questions at the end. Over to you, Mike.
Thanks, Anthony. Permeable paving plays an active part in SUDS. The term SUDS covering a whole range of applications, such as filter strips, swales, infiltration basins, wet ponds, detention basins, wetlands, filter drains, soakaways, green roofs, rills, and of course permeable paving. Each element of SUDS is designed to slow down and imitate the natural course taken by surface water, which is to gradually enter the ground, replenish natural water courses, and avoid any impact caused by sudden flooding. The issue with impermeable hard landscaping surfaces is that water quickly runs off, is usually directed towards gullies and channels, etc., which in turn overloads existing drainage systems, causing flooding. Now, to reduce the flooding impact and subsequent pollution of watercourses, new legislation was introduced on the 1st of October 2008, and it's now a requirement that planning permission is essential for the construction of a new driveway or an extension to an existing driveway which exceeds a total of 5 square meters, unless the new replacement driveway uses a permeable or porous surfacing. Now, this can be gravel, permeable concrete or clay block paving, or a porous asphalt with a permeable resin-bound surfacing included in this. Or if the rainwater is directed to a lawn or a border to drain into the garden naturally, or directed towards a suitably designed soakaway within the property's boundary. So to clarify, if the impermeable surface exceeds 5 square meters, planning permission will be required if surface water is discharged directly onto or into the public highway. So what we're discussing tonight is based upon the 2 standards, BS 7533 Part 3, which deals with the basic principles of good construction techniques, and Part 13 of the same standard, which is a 26-page comprehensive document dealing specifically with permeable pavement design and construction, which we hope to explain. We're experiencing an increasing rate of flooding throughout the UK, with very recent news reports of areas in London being severely affected, and hopefully the illustrations above explain the reason for this. Land in its natural undeveloped state directs only approximately 5% surface water runoff into natural watercourses, with 95% naturally infiltrated into the subgrade. In farmland, surface water runoff is affected by the agricultural process and compaction of the surface by livestock, increasing water runoff to 30%. Suburban areas begin to seriously reduce surface water naturally entering the subgrade, as the vast majority of domestic driveways are impermeable, the surface water runoff directed and dealt with by public highway drain systems. So these become overloaded during periods of intense or prolonged rainfall. And in towns and cities, apart from specific green areas such as municipal parks and green open spaces, etc., some 95% of surface water enters drainage systems and watercourses, with many of these not designed for the increased development that we now see. So this has instigated the need for controlling this water at source to ease the burden on these drainage systems and watercourses. Now, the three key principles of SUDS and permeable pavements are that it improves water quality by filtering pollutants from the water flowing through the system. And it reduces water quantity by imitating the natural processes to deal with excess water, but by providing control at or very close to the source. It also deals with volumes of water by keeping surfaces clear of standing water and slowly releasing it into the ground or into traditional systems at a controlled rate, and that's the key. And biodiversity benefits by sustaining the local water table, helping to maintain flora and fauna, and amenity improves as permeable paved surfaces carries out the necessary drainage function, but also provides usable spaces such as car parks, in particular to commercial and housing developments, where these areas can be thousands of square meters, such as in residential parking and supermarket car parks. If we start looking at the basic design of permeable pavements, there is some similarity with traditional flexible construction, but using different components. It's important to recognise there are two factors which determine the depth of subbase required. One is the structural requirement, which determines the pavement strength required to accommodate the anticipated traffic loadings and takes into consideration the type and strength of the subgrade. Secondly, the hydraulic requirements, which provide sufficient capacity to allow the water permeating through the surface into the subbase, and the need for this to be temporarily stored until either it permeates naturally into the subgrade or is held until dispersion is complete, or alternatively stored as part of an attenuation system for grey water use, etc. If we consider this diagram as the basic principle providing total infiltration, or a system A as it's known, surface water permeates through the wider joints, nominally aiming for a 6 mm gap to allow the 2 to 6 mm coarse graded aggregate to be brushed in, passes through the lane course, which uses the same 2 to 6 mm CGA, and flows through the permeable subbase, eventually entering the subgrade. These different layers are separated by a geotextile, generally a woven or non-woven material. And the job of the geotextile is to allow water to flow through and prevent migration of particulates between the construction layers, whilst providing a trap for any sediment. The geotextile reduces the rate of infiltration and is required to perform both structurally and hydraulically. All coarse graded aggregate within the system, which we'll address later, is clean, no fines, and angular, allowing the controlled free flow of water through the system. Now, the depth of the subbase is designed subject to both the hydraulic and loading calculation requirements, which we will discuss shortly. And it's often the case where the more substantial depth of subbase is a prerequisite of the hydraulic requirement. Just something I wanted to mention here is if the total depth of excavation required provides to be a problem due to levels, there is an alternative option to use a subbase replacement system, which can provide a shallower excavation. And basically, this is a geocellular box system incorporated into a permeable pavement, consisting of plastic cellular units connected together to form a raft structure. For those who may not be aware, this is if you've been on sites and you've seen like an upturned plastic milk crate, it's that sort of structure. And the main advantage is that they have a high void ratio, which compared with granular subbase can reduce the overall depth of subbase by some 30 to 40%. So this is useful in reducing the disposal of excavator material to landfill, making these systems particularly suited to the economics for brownfield and contaminated sites. Now, if I go through the three main systems, System A is always known as the total infiltration system, and this allows water to permeate through the pavement, to infiltrate down through the joints between the pavers, passing directly through the constructed layers below and into the subgrade. Now, some water may be retained temporarily within the subbase layer, particularly following a heavy downpour, allowing temporary storage before permeating into the subgrade. System A provides zero discharge into traditional drainage systems, so it does not require any gullies or any pipe work, usually associated with drainage works. System A is used where the subgrade provides good permeability and subsequently good strength. System B, which is partial infiltration, is similar to System A. However, this method requires a series of perforated pipes laid upon the geotextile immediately above the subgrade. And this allows excess water within the subbase layer to be directed towards a sustainable drainage systems or permitted drainage outlet. System B can be used when the existing subgrade may not provide sufficient permeability. System C, with no infiltration, is designed to provide complete capture of the water using a flexible impermeable membrane laid directly on top of the subgrade and to the sides of the subbase, so effectively forming the storage of water. Consequently, perforated pipes are placed directly on top of the membrane, directing water to permitted sewers or watercourses or treatment systems. System C is used in situations having low permeability, usually associated with low strength subgrades, where additional water infiltrating this type of subgrade would result in damage and consequential failure. This system can also be utilised for water attenuation or water harvesting, where the stored water can be cleaned, reused and for other purposes, example grey water and also irrigation. And the system is also suitable for contaminated or brownfield sites to prevent pollutants being washed into the subgrade and eventually introduced into existing natural watercourses. So if we compare these diagrammatically side by side, in the cases of systems B and C, you will observe that careful consideration must be given to controlling the outflow from the drainage pipe, particularly in system C, as this is the only way water leaves the system. The volume or rate of water entering a permeable pavement is often greater than the rate percolated into the subgrade or being slowly discharged to a secondary system via the drain pipes. Consequently, this requires the volume of water required to be stored within the subbase to be calculated, and it's necessary in types B and C to adopt a flow control device limiting the discharge from the drainage pipes into existing systems, as no restriction would result in overloading the receiving system, particularly in the case of prolonged heavy rainfall. This restriction of flow through the overflow pipes requires calculation, as it may be required, for example, to be 5 litres per second per hectare to prevent overloading the drainage system it enters. So basically what we're saying is water in minus the water out equals the storage volume that's required. Now, assessing the subgrade suitability, the type of subgrade determines the permeability and which type of filtration system, system A, B or C, is most suitable. Permeability can be generally determined by a soil description or a CBR value or a plasticity index. Now, just to explain, in case these terms are unfamiliar, CBR is an abbreviation for the Californian bearing ratio and is used to determine the strength of a subgrade. And basically, it's a method of applying pressure from a known diameter plunger directly onto the surface of a prepared soil sample. This resistance is measured by the deflection on a cylindrical ring, and this test is prepared and carried out in the soils testing laboratory. So basically, anything 2 to 5% indicates a heavy clay, 5 to 20% a sandy clay, with 30 to 80% being a well-graded sandy gravel. Now, the term plasticity index determines a type of clay and differentiates between clay, silty clay, and a sandy clay. All these associated with having low CBR values of between 2 to 20%, and these being possible problematic subgrades. From recommendations suggested in BS 7533 Part 13, it suggests for a type A and B system, the anticipated thickness of subbase, specifically for a domestic driveway, would be 350 millimeters thickness. But this guidance is only suitable for subgrades with a CBR greater than 15%. So for a CBR less than this, the subbase will have to be increased, and we would suggest employing an engineer to do these calculations. For a type C construction required on a clay subgrade with a CBR value less than 15%, where no water is allowed to enter the subgrade and water from within the system is dispelled through the water overflow pipes, the subgrade needs to be strengthened by an additional 150 mil improvement layer. And this is a layer of stone at the top of the subgrade to improve the foundation for the construction of the permeable pavement. So to try and associate a soil description to a corresponding CBR value and which of the three systems are most suitable, basically what we're saying is that for a heavy clay and a silty clay, the only option is to use system C, as water will not permeate into the subgrade. With a sandy clay, there is still insufficient permeability for it to drain freely without the added assistance from drainage pipes. For a poorly graded sand, a well-graded sand and sandy gravel, any system may be used. In a free draining subgrade, system C can be adopted if water contained within the system enables it to be used as a source of grey water. So you're effectively creating a reservoir, or where there's a possibility of the subgrade being polluted or within 1 metre of the water table. Where the water table is not within 1 metre of the formation level, then type A and B can be adopted. Though large commercial and housing projects may demand the need for a comprehensive soil investigation to establish the subgrade strength and permeability in order to provide adequate hydraulic requirements, so preventing expensive flood damage, there is a useful test to quickly and inexpensively determine if the subgrade in a domestic application is sufficiently permeable, based on the stated BRE Digest 365 test procedure, which is for soak-away design. From the British Standard 7533 Part 13 guidance notes, it suggests from design tables that a minimum of 1 times 10 to the minus 6 meters per second coefficient of permeability for a type A system. Now, this sounds frightfully technical and complicated, but there is further guidance in the standard where you're able to derive from tables that this means a free drain in sandy clay having a CBR value of 15% or greater. However, any concerns, particularly relating to construction on subgrades of questionable performance, i.e. clays, it would be beneficial to involve an engineer. So what would you be expected to provide to an engineer? And I'll break down the headings above in turn. So details of traffic loading. The vast majority of driveways will be for the family car, on average 1.5 tons. However, it may be worthwhile considering future-proofing the design by considering the possibility of 4x4 vehicles or light commercial vehicles, etc., which may approach 2.5 to 3 tons. And for this, you would definitely require a paver attaining a T4 transverse strength. Stone return periods, there is a geographical map of the UK which shows average rainfall and anticipated storm periods. And this information is used within the overall calculation to determine the depth of subbase for water attenuation reasons. And the design engineer will have this information to hand. Infiltration rates and allowable outflow rates, this is determined by the type of subgrade, which governs how quickly the water permeates the ground. So typically a gravelly, sandy soil drains a lot quicker than a silty clay. Allowable outflow rates are determined by the local authority and how much water is allowed to enter their highway drainage systems. We've already seen in systems B and C where an overload pipe is incorporated, the outflow rate of these pipes carefully controlled with holding the water within the construction, so restricting flow into the drains. CBR data, this is the figure expressed as a percentage we've already covered. Ground conditions, contaminated soil. It's highly unlikely that this will be an issue on an existing driveway and properties. However, this should this be a brownfield site, which may contain contaminants, water permeating through this into natural water courses will need to be prevented by using a System C construction. Drawings, level information, site location, etc. enables the designer to further understand the requirements of the site. And climate change considerations. This is currently topical at the moment, with many making political fodder from it. So I'm not even going to go there. However, as the design life maybe 20 years, rainfall patterns may change over this period, affecting current storm return periods. So there may be a requirement to consider a degree of future proofing. To look at the subbase specification, this is directly from the British Standard 7533 Part 13, which is specifically for permeable paving. Firstly, the civil analysis result shows the lack of fine material within the mix, which of course would cause clogging of the system, and clearly this is not an MOT type 1. Secondly, all granular subbase material must be crushed rock or concrete possessing well-defined edges. This provides good interlock of the aggregate. As previously mentioned, it is recommended a minimum depth of 350 mm should be used for a subgrade achieving a CBR of greater than 15%. However, this depth may be varied at the discretion of the engineer. For increased depths of subbase, a lower subbase layer can be introduced, which should consist of a 10 to 63 mm clean crushed stone. Laying course and jointing material, similarly, the British Standard also describes the laying course and jointing material. This is not sharp sand bedding and a fine dry jointing sand. Once again, it's important to recognise the description of the materials, but I want to draw particular attention to clean crushed stone, typically limestone or granite. Gravel is not permitted, and by this it means a crushed rounded gravel, and the next slide explains why. This is an actual experience from a few years ago I was involved in. The image on the left is the correct specification of material, being angular, crushed rock, meeting the requirement or the required BS sieve analysis test. In this particular case, being a crushed Leicestershire granite. Now, the image on the right is clearly a naturally occurred crushed gravel, which met all the sieve analysis requirements. We were 90% through supplying a site when I received a request from the landscape architect to attend a site meeting, stating how paving was moving when being driven over by the site JCB. Now, this obviously raised great concern as to why the pavers were assuming a wave motion when being trafficked, but it wasn't until the contractor was instructed to unzip an area of the paving that the problem was recognised, the wrong material having been used, and that is a crushed gravel and not the material as specified. The rounded shape of the gravel produced no interlock, and as a consequence, the pavement surface adopted a fluid motion. So what does a permeable clay paving surface look like? The left-hand image shows a standard clay paver laid on edge with a spacing between adjacent pavers of about 6 mil. And the right image shows the same area where the joints were partially filled with the 2 to 6 grey coarse graded aggregate, and the top 25 to 30 mil of the joint filled with a 2 to 4 millimetre red-brown crushed Scottish granite to complement the paver colour. Just to compare the conventional flexible paving with flexible permeable paving, the top image shows a typical flexible application laid to falls where surface water is directed towards the drainage channel. And should there be any low spots, then water will accumulate and puddle. In comparison, permeable paving can be laid flat, will not puddle, and dries quickly. A question I'm often asked is, can permeable paving be used on a sloping drive? The answer is yes, but with the following considerations. In System B, where there is a reduced rate of permeability into the subgrade, and System C, where there is no permeability at all, water will naturally accumulate at the lower end, which will reduce the storage capacity of the overall system. You will also see water coming up through the joints as the system starts to fill up. In the case of both B and C systems, it is recommended to have a minimum gradient of approximately 0.5% towards the drainage pipe outlets. And this is equivalent to a 50 mil fall over a 10 metre length, or 1 in 200. For a sloping site or a sloping driveway where the gradient exceeds 5%, which is 500 mil over a 10 metre length, or 1 in 20, the terraced or compartmental sections are created by incorporating check dams which restrict the flow of water from higher to lower sections by utilising the storage capacity available in the higher sections. The concrete check dam can also be used as a lateral restraint to prevent the movement or creep experienced with flexible paving when subject to heavy channelized braking, typically experienced at the bottom of drives in any form of flexible paving. The top face of the check dam can be either exposed at the surface or a double row of pavers fixed directly to the top of the concrete to make it visually more attractive. An impermeable membrane is required for System C only, where effectively a tank is formed using typically HDPE, polypropylene or EPDM membranes. However, it is recommended to incorporate an impermeable membrane up against a building or wall for types A and B also, as above. These membranes should be durable, robust and capable of loads applied during the construction process and throughout the full design life of the pavement. They should be able to resist puncture and stresses and strains associated with movement and environmental stress cracking, and also unaffected by potential pollutants present in groundwater. The strength, suitability and performance also applies to geotextiles, separating the different layers. Particular attention has to be paid to this detail, especially in older properties where there may not be a DPM, or over the years where it may have been compromised. There is also a likelihood that the new depth of excavation to accommodate a permeable pavement may exceed the original depth of any existing drive, so it would be wise to adopt the detail above to prevent any ingress of moisture back into the building and turning an existing cellar into a plunge pool overnight. Can permeable pavements flood? Well, yes, but all drainage systems are designed around the possibility of not being able to cope with a 1 in 30 or a 1 in 100 year storm occurrence for economic reasons. Designed correctly, permeable pavements are calculated to block by as much as 90% over the design life of 20 years. And as is stated in the slide, will still perform if only 10% of the system remains working successfully. But I just wanted to draw your attention to avoid dumping a delivery of sand or topsoil tipped directly onto any permeable driveway, as the fine particles will block the joints and possibly drop into the subbase. I have seen where permeable paving maintenance has been described as requiring a reactive maintenance regime, which I think is a fair statement, in so much that the system will only need attention if it no longer works. We would recommend removing moss, weeds with an application of a safe weed killer, and the removal of general detritus by sweeping of the surface to maintain the cosmetic appearance. If ponding of the surface is noticed, then simply remove the aggregate within the block joints with either a jet wash, stiff brush, or suction sweeper, and replace the aggregate. Now, there are a few sort of frequently asked questions that we get thrown at us. I've just listed a few here, and hopefully you'll have a few more questions for us. Can permeable paving be used on clay soils? Yes, as previously discussed, it's typically a system C that would be most suitable. Is it damaged by frost freezing conditions? No, it's highly unlikely the water within the subbase will freeze due to the depth of the subbase beneath the surface, and the whole construction is flexible and will accommodate any ground movement successfully. Does it clog? Possibly, if mistreated, but hopefully we addressed this previously. And one of the favourite questions, is it expensive? How does it compare with normal paving? And it's difficult to draw a direct comparison with traditional flexible paving, as drainage channels, gullies, inclusion of manhole constructions, soakaway construction, connection drain facilities, etc., need to be factored in to a traditional flexible construction, as these are not required by a typical System A permeable construction. Is there a lack of aesthetic options? Though the concrete manufacturers have led the field in permeable pavement development for over 20 years now in small element block paving, clay is now a viable option. The use of either clay, concrete, and natural stone as a permeable pavement is governed by exactly the same British Standard 7533 Part 13. So we think the onset of clay now provides you with a visually more appealing and durable product, and it doesn't fade. So please accept that the information we've got, it's a very, very condensed version of the actual document from British Standards. And it's offered in guidance only and outlines the design process and what you have to consider. But the whole process is easy to follow. There is a process of design with useful tables to consider and lead you through the design process. Chelmer Valley don't offer a design service as such, but there are companies out there who do, but we are here and happy to offer any advice we can. Just open it up now if there's any questions.
Yeah, we've got a few come in, Mike.
That's good.
So just on those frequently asked questions as well, there was a little tab about to point or not to point. So,
oh yeah, sorry, yeah, forget about that one. Yeah,
that's all right, mate. That's all right. So yeah, it's not really relevant to this evening, but it's a question we get asked a lot, and we thought we'd cover it just really quickly tonight.
Yeah.
Essentially, if you're going to point, we recommend to have a rigid installation, ideally with a concrete base. For using type 1, that is still classed as flexible, so we would recommend a concrete sub base. In terms of pointing, I would recommend flow point. So that's a cement-based slurry pointing. We've seen really good results with it and works really well with the pavers. Stuff like GFTK, obviously it still has that slight permeability to it, so it would probably lend itself better to a slightly flexible system like type 1 and mortar. But yeah, true rigid installation, I would say, a concrete sub base, mortar bed, and then flow point should work roughly.
Yeah.
Obviously, if you're doing a cottage, cottage garden bricks, like a traditional brick patio, then obviously you might do a weather struck, normal sand and cement pointing. But in terms of slurry-based ones, flow point is the one we've seen good results from.
Yeah, if I can just add to that, and it is very important to bed the pavers on a full mortar bed onto the concrete base. And what we recommend is what we call a designation 2 mortar mix. And all that means it's a slightly stronger than traditional sort of brickwork mortar, in that it's a 1:3 cement sand ratio. And that just gives it extra durability, because in paving, it would be constantly wet or damp and open to, less sheltered situation than traditional brickwork would be. That's the traditional way of doing it, using and the same mortar mix, designation 2 mortar, in the joints as well. Now, the traditional mortar is a bit restrictive, because it needs to be an 8 to 10 mil mortar width or joint width to enable the guys on site to be able to ensure that mortar width or that joint width is totally full of mortar. The advantage with flow point is that you can close those joints up, and I believe you can actually, the minimum joint width is possibly 3 to 5 mil, and with flow point being a mixed to a thick cream consistency, and it flows into the joint itself, make sure it's fully full. And you can get that joint width down to a lot less than traditional mortar. So that's one advantage of the flow point product.
Cool, thanks, Mike. So first question from Sinead Royale. How do you find where a water table is?
Good question. I think the only way to do it, and this does, the problem is it varies throughout the year. And obviously in winter, the water table would be higher. The only way to establish it is to dig down until you'll see a definite change in the moisture content of the subgrade. Locally, you may have builders who often build in that specific area that say, nah, you'll never hit the water table in this area, or yes, be careful of the water table being fairly high. A good indication of a high water table is naturally occurring springs as well. So yeah, it depends what time of the year you dig down, and it might be dry in summer, but in winter you may see this water coming up through.
Cool. Right, next question is from Michelle McDonald. Would a slope away from the road change the needs for a deeper subgrade? Would planning authorities take that into account? Sorry,
say again, Anthony. I missed that.
So would a slope away from the road change the needs for a deeper subgrade?
A slope away from the roads?
Yeah, so rather than the driveway sloping towards the pavement, sloping towards the house.
Oh, right. Okay. Yeah, if it's sloped towards, and we're talking about a permeable pavement here, yes?
Yes.
Right. If it's sloped, so. Yeah, if it's sloped back towards the house, then obviously at the low point with a permeable pavement, you would have to accommodate that water somehow, somewhere, either into a soak away, if it's it's a bad ground. If it's a good permeable subsoil you're building on, then yes, that will the surface water will percolate through the pavement, the permeable pavement, and dissipate into the subgrade, providing it's sufficiently adequate enough for it to do that. If it's sloping towards the house, then follow the leads with the on a sloping drive. If it's a fairly steep slope from the back of footpath towards the house, then you may have to incorporate check dams to prevent it all going down towards the bottom end near the house and possibly leaking under the garage door, etc. But if the client there has got a specific requirement, wants us to send a drawing in, we'll gladly have a look at that and give our specific recommendations.
Brilliant. And as Mike said, Michelle, I hope that answers your question, but if there is anything more specific, just get in touch and we'll be able to answer it for you. So Nancy Rogers says she'll have to leave, but she'll catch the recording. So with regards to digging the hole, the 400 by 400 hole, to test the drainage of the substrate, how long do you have to leave it?
Sorry, I missed that off the slide. I think it's a good indication to come back after 24 hours. Now, if you've still got water in that hole after 24 hours, I think you can sort of satisfy yourself that that's not quite sufficiently permeable enough. But fill it up a number of 3 times, and if that water is being held on the 3rd time of filling up, I think you can safely assume that that's not really suitable for a type A or full infiltration system.
Cool, thanks, Mike. So I'll probably answer this one, but it's from Emily Ross. Do Chelmer Valley have any associations with engineers that you can recommend to carry out all the tests that you have mentioned? So we actually spoke about this the other day, Emily. We don't at the moment, but subject to us doing this webinar, we've realised that it would probably be a good thing for us to have. So we are going to start to look into that. I'm sure you can appreciate recommending someone for something like that. We need to do our homework, basically. We can't just do a Google search and come up with a list. We need to vet these people and make sure they're credible to put forward. But we are definitely going to look into that. And we'll come back to everyone with that once we put that list together.
Hi, Emily. Good to hear from you again. What I would perhaps favour would be, if there's an engineer within your particular geographical area who's got a better working knowledge of that particular soil type or rainfall, in the sort of Liverpool or Manchester area, and they would be more conversant with normal topographic situations and knowledge of the soils in that specific area. But it is something we have been speaking about, as Anthony says, that we are looking further into.
Yeah, and from Emily again, I think this has been covered in the presentation now, Mike, but do you get a build-up of particulates and debris getting into the joints over time, and how do you deal with this? So I think we've covered that, but I don't know if you want to go into it. The general, naturally occurring dirt and detritus in the atmosphere, or washing off the car or being brought onto the driveway with the tires. Yes, it will start to fill up the voids, but as I mentioned, because it is actually over-engineered. If it clogs up to 90%, the 10% will still allow it to work. But if there's a catastrophic, where a soft landscape and embankment, falls onto the permeable drive, worst case scenario is that you can, if it fills all the joints up and stops it working completely, worst case scenario is that you can unzip the pavers, stack them on one side, replace all the coarse graded aggregate that was in the joints and the bedding, and of course that should then stop at that geotextile. So it's a case of stopping at the geotextile, cleaning that off, or perhaps replacing it if it's really bad. And then just using the same pavers again and relaying it on new bedding material and new jointing material. Yeah, I think it would take an awful lot to do that.
Yeah.
And as Mike says, it can be blocked up to 90%. So it's normally not an issue, but if it is, you can lift and relay essentially.
Yeah.
So another question from Sinead Royale. How deep down should the impermeable membrane slope out from the building walls? So the slide you had there, Mike, with the membrane next to the building, how far should that come down and out? It's
important to sort of tuck it underneath or place it from the side of the building and place it on top of the formation layer, and then the sub-base material built on top of that.
I
So
mean,
any water that's contained in the sub-base, it's that water containment that you need to prevent going back into the building.
Yeah, I mean, how far away would you project that from the building?
I think there's actually a figure on the drawing.
Is it an angle rather than a projection?
Yeah, it's an angle. If you aim for, it's just to prevent the water sort of leaching back into the building. If you know, a 45-degree angle is always safe, and then you know from the building outwards underneath the sub base. But I think if you look at that diagram, I think it does actually say is it a meter or 2 meters underneath the sub base.
Okay, right, brilliant. And also with the land drains on systems B and C,
yeah.
Could you just go into a bit more where they actually go to? So we've got another question from Sinead. Just where those land drains would run to, basically.
Yeah. Normally, if the ground that the buildings or the driveways on isn't sufficiently permeable enough, this is why you adopt the Type B or the Type C system. And the overflow pipes, we need to get rid of that water somehow. And the main reason of doing that is to direct that into a highway authority drain or a soakaway that's constructed somewhere else on the property. So it is an overflow pipe, but if you do tap that into the local authority drain, it must fulfill their requirements. And I think I mentioned it's something like 5 figure of 5 litres per hectare per second, and that's so it doesn't overflow the existing highway drain. So it's a safety device, if you like, for a Type B and C type construction, but you will need permission from the local authority if that overflow has got to go into their system. But what it does do is reduce the amount of water going in at any one time, and that's why it's restricted or retarded. So you don't get that sudden rush following a downpour that overloads the local authority drainage system. It's sort of backed up or reserved within the construction, and it slowly trickles out into their drains instead of gushing through as it normally would do.
Okay, brilliant. Thanks, Mike. I've got a question here from Douglas Dalgleish. Is 5 meters the minimum permissible distance between a soakaway and the house, and from soakaway to the property boundaries? No.
I don't know that. I think that would be dependent on in each and every local authority and building control. I would check with your local building control on that.
Okay, brilliant. And I think that is everything for the questions. Does anyone have any further questions they'd like Mike to answer whilst we're here? Obviously, we are always contactable, and we can always put you through to Mike to answer anything you need. Okay, forever hold your peace. Brilliant. So yeah, thanks everyone for attending.
Thank you.
I know it's your own private time, and obviously we're all very busy people this time of year, and the landscape industry's gone absolutely crazy. So thank you very much for attending, and yeah, we'll get the next one. We'll get the next one lined up. Take care, everyone.
Thank you. Good night.
Cheers, everyone. And also, a recording will be, a link will be sent out for the recording as well, just in case you need to pass it on to anyone.